So we already know the notion of a random variable together with the corresponding probability mass function and probability density function, discrete and continuous case. And in both cases, we have the notion of cumulative distribution function. Next, we will study some numerical summary for the random variables. And the first such thing is expectation. Expectation of a random variable, in fact, this is the name of the value which we expect most of all to get from the random variable. Again, how we can find the expectation? We already know that, for example, in discrete case, we have the probability mass function, which can be drawn or given by a table like this. And the expectation is the number, this is just one number, we denote it by E of x, expectation of this random variable. Sometimes we also call it expected value. This is a sum of the products of all possible xi, the values, times corresponding probabilities. In fact, this expectation, usually we call it mean also. And in fact, if all the probabilities are the same, so if all the values are equally likely, we just get average value. Let's consider example for the machine breakdowns. Remember, we had $50 with probability 0.3, $200 with probability 0.2, and $350 with probability 0.5. So how we can find expected value of cost? We take all possible values of cost, 50, 200, and 350, and multiply it by corresponding probabilities and sum all of them. We can calculate that overall we get 230. So if we look at this graphically, 230, it's somewhere here. So this is the value. It's not in the values of cost. You can notice it's not in among these values, but it shows us that we expect to get usually the values close to this. For example, if you see that 200 is the closest value, then this is the thing that we expect closer to 200. Okay, let's move on to some more examples. So power plant operation. What we had there, remember, we have the values for the random variable, which calculates the number of plants generating electricity, 0, 1, 2, and 3, and we calculated corresponding probabilities, right? So we multiplied the values times probabilities and sum all of them, and we get 1.76. Again, if we draw it on our x, which has 0, 1, 2, 3 values, then you see that it's closer to value 2. So this is what we mostly expect between 2 and 1. Okay. Next, the game of chance that we get. Remember, we consider the difference, the positive difference of the values on the two dice. And remember, we had the value 0, 1, 2, 3, 4, and 5. These are possible differences. And the corresponding probabilities, so here they divided by 36. So we take the values multiplied by corresponding probabilities. When you already have drawn probability mass function, this is very simple. You just take value times probability plus value times probability, value times probability, and you can do this very quickly. And when you sum all of them up, you get, in this case, 1.94. So this is approximately somewhere here. It's shown on the picture. So this is, you may mostly expect the differences between 1 and 2. Okay, so closer to 2. All right. And okay, here we have some question. So expected value, this is the value which we, let's say, expect to get from a particular experiment. Okay? So suppose that we organize some game where player roll 2 dice and you pay the player the dollar amount of the difference in the scores. So for example, if he had difference 2, we pay him $2. If he had different 4, we pay him $4, and so on. So how do you think how much you should charge a person to play in this particular game? Of course, we want to get some profit. We don't want to lose anything after some many games. Okay? So what do you think? How much we should charge a person to play? So what should be the cost of this game for a person who want to play? And since we expect on average to get 1.94, then of course it's reasonable to get, since we want to get some profit, so this will be our small profit on average in each game. So we can say, let's make it $2 per game. Okay, if you make it smaller than $2, then you will lose after many games. If you make it larger than $2, of course the profit will be larger. So it's more or less reasonable to charge $2. At least $2, right? Okay, let's move on to some more examples. And again, we have the same notion for continuous random variable, the same name, expectation, and for expected value for discrete case, we had the sum of pi and xi. These are probabilities times corresponding values of random variable. So the same meaning is here, but in continuous case we replace sum with the integral, probability with the density function, and xi, the values just will be denoted by x. So you see that expected value is the integral over all possible values, x times the probabilities. Okay, and we also have something for symmetric random variables. If a random variable is symmetric, then the expected value is just mean, just average. So just the midpoint, in fact, for the function. Okay. For example, this is example the metal cylinder production. This is example of symmetric random variable, and expected value will be exactly in the middle of this interval. And you can check that this is indeed true. If you integrate this function times x, this is probability density function which we are given, times x over this interval, over the whole interval, if you calculate it, you get exactly 50 millimeters, which is in the middle. Of course, it doesn't hold for the case when the function is not symmetric. For example, the battery failure times the function is like this. And if you calculate the expected value, this is integral from 0 to infinity, x times the probability density function, which is again given. If you calculate this integral, you get just 1. You can check that the integral is 1. So this is the expected value for this case. We expect to get 1 hour for battery, not so good batteries, right, in this case. Next, we look at the game of chance, and here, as you remember, the probability density function was a flat function, and so this is symmetric, right? And so the expected value is exactly in the middle of the interval of the values, the random variables. And if you try to calculate it, this is integral over, let's say we look at the x random variable, the winning, from 0 to 1,000, x times, this is our f of x, the density function. If you integrate, you get exactly 500, which was expected, right? What I want to also add about the expected value is the following result, which is very important and will be frequently used during the course. So first of all, the expectation can be extended from not just one variable x, but to some expected value of a function of x. So this can be exponent or some linear combination, whatever. And the idea is just the same. And if we do this, we have the following result. Expected value is, in some sense, linear function. So what does it mean? If you take some function u1 of the variable, another function u2 of the variable, and multiply them by constants, and want to calculate the expected value of this linear combination, then you just can move these constants outside the expected value and sum as well. So you can find it as finding expected value of the first function, expected value of the second, multiplied and summed together. Okay, this is very important theorem, and please try to remember this now. I will remind it anyway several times during the course. Another important numerical value for the random variable is median. What is the median? This is, in some sense, the following. Okay, let me just show you how it looks like on the graph. So let's say you have some f of x. This is your density function, right? And we know that the probability, for example, from a to b, this will be just area under this from a to b interval. And sometimes we're interested what is the point here, such that if we look at the area to the left and to the right from this point, they will be equal to 0.5. So in fact, what we ask, so first of all, this point is called median, denoted by small m. So what we ask, find the point such that we get 50% to the right and 50% to the left from this point. In fact, this is half of the probabilities. With half of the probabilities, the values will be larger than m, and with the half of the probabilities, the values will be smaller than m, right? So, and we call it median. How we can find it, since we know that the cumulative distribution function is the area on the left from this m, we can say that median is exactly the value such that the cumulative distribution function at this median is 0.5. So if we know cumulative distribution function, then we can find the median solving this equation. And for the symmetric random variable, the median coincides with the expected value. So mu is equal to median for the case of symmetric random variable. Okay? So they are different only if the function is not symmetric. Let's have a look at this example. This is the battery failure time example. And remember, we found the cumulative distribution function for this example. And how we can find the median? We have to solve the equation. This is equal to 0.5. It's always 0.5 for median. Okay? And if we solve it, we can use also, for example, Wolfram alpha to solve this equation. And we get 50 millimeters if we write millimeters. Sorry, this is metal cylinder example. Yes. Sorry, this is metal cylinder example. This is different from this picture. Okay. Let me draw it somewhere here. So for the metal cylinder example, remember what we had? It was symmetric, right? It was just parabola. And we get 50 millimeters for expected value, and we get the same for median, right? It's not surprising because from this point we have half on the left and half on the right, because it's just symmetric. Okay, and if we look at this example, which is not symmetric, you can see if we solve this equation, again we take the cumulative distribution function and make it equal to 0.5. If we solve it, we get this number, 0.414. Okay, if we put this point on the line, we get that median is here. Expected value was 1, right? So median is smaller than expected value in this case. So we have half on the right and half on the left from this point.